Alright guys, so for this video we're going to talk about how to do polar integrals. Previously we talked about derivatives, so of course now we're wondering how do we do the integral of a polar function. So we're going to think about this, of course, in terms of area. But before that, I want to talk about a geometry thing. How do we find the area of a sector of a circle? So what I mean by that is if we have a circle, and this circle of course has some radius r, and we want to find the area of just one section of it, like this pink region right there, how do we find it? Well, let's think back to them. We're going to do this to help us come up with the formula for how we solve this problem. Okay, so if we just wanted to find the area of an entire circle, so the whole circle, of course, is just pi r squared. Now in this case, we're saying, well, what if we just have a section of the circle? So instead of taking the whole circle, we just have a sector with some angle theta. Okay, now this blue sector, this pink sector, is basically going to be a fraction of the whole circle. And what fraction are you going to have? Well, that fraction is going to be the angle divided by 2 pi times the whole circle. So this is the circle, and this is basically saying, what fraction of that circle do we have that we're trying to find the area of? Okay, so if we want half the circle, we have theta would be pi, so we'd have 1/2 times pi r squared. So that's where the formula comes from. So anyway, if we simplify this out and cancel the pi's, this becomes 1/2 times theta times r squared, and a lot of times we'll write that as 1/2 r squared times theta. Now, the reason we're doing this is because now this is the geometry. Now we're going to start doing some calculus. Is if we want to find the area of a polar curve. And when we find area of a polar curve, we're not going to go left to right, right? We don't think of polar in terms of left to right. We think of a starting angle and end angle. So the area of a polar curve from some theta 1 to theta 2, so a start angle to an end angle. And what that is going to be is it's going to equal 1/2 r squared times d theta. So we're going from theta 1 to theta 2. So this is a crucial formula. Put a box around this, save it, whatever you got to do. But this just tells you what is the area of a polar curve from one angle to another. You integrate 1/2 r squared times d theta. So what that means is that that's the situation where we have some curve that looks like this. So this is some r, and we're starting from some theta 1 to some theta 2, so a start angle to an end angle, and we're finding this little area of the region inside there. And again, this isn't just a random formula, right? This came from our area of a circle that we got in geometry that you probably don't remember, the 1/2 r squared times theta. We're basically just integrating that. We're integrating together a bunch of tiny little sections of a circle, and that's where this formula comes from. So it's not rectangles, which is why we have a slightly different formula here. So from a graphical sense, here's what we're doing. Let's say this green curve here is a polar area. So let's say we wanted to measure from angle 0 to some other angles. So what we'll see is as we look at the angles, those are the area, oh gosh, it's going out of control. But those are the areas that we're finding. So if we want 0 to pi over 3, we're basically, or whatever's past that, we're basically just taking all these little sections going out and integrating. So notice we're not doing a top minus bottom. It's not rectangles. We're going straight up from the origin to the curve in that sense. So that's where that's going from. So that's the area that we're trying to measure. And then the formula we're using is this. And this is, again, a key formula. Okay, let's do some sample problems. So let's find the area of the circle r equals 3. Find the area of that is enclosed. Okay, now you guys know that is a circle of radius 3. So we have, it's saying the radius is always 3, so it gives us a circle. Now, in geometry, of course, we can look at this and just say, hey, the area is pi times 3 squared, which is equal to 9. Correct, pi. Okay, good. But in terms of calculus, if we want to go all the way around, so we're saying we're going to start at 0, and we're going to go all the way around until we get back to 2 pi. What we're going to do in that case is we're going to go integral 0 to 2 pi of 1/2 times the r squared, which is in this case 3 squared. So I'm just plugging in this formula for r d theta. Now, one thing I actually wanted to talk about, when you're measuring angles, you always want to go counterclockwise. There are no real exceptions to this rule. When you're going from your start angle to your end angle, you want to make sure that you're going in that direction. You never want to be going backwards. That's going to bring in some different problems. So make sure you are going in a counterclockwise fashion as we go from our starting angle to our end angle. So again, this is our start angle, this is our end angle, and we're going in a counterclockwise fashion around. Okay, anyway, let's go back here and do the calculus. Usually the 1/2 comes out in front, so this is just 1/2 integral 0 to 2 pi of 9 times d theta. Now, of course, that's a pretty easy integral to do. Usually we just leave the 1/2 out in front. So that's just 9 theta going from 0 to 2 pi. So when you plug that in, you just see this is 9 pi minus 0, which is 9 pi. Great. So calculus gave us the answer that we expected that we were going to get. Terrific. So let's do a couple other examples then and see what we can do. Okay. So now, suppose we want to have the area of r equals 2 sine theta from theta equals 0 to theta equals pi over 4. Okay, so let's see. I mean, it's always good to like draw a picture. I always just recommend drawing a picture. I know what this looks like. If you don't, you could just go to your graphic calculator, right? So we'll go to polar mode. Oops, we got to turn it on. So we turn this on, we'll go to our polar mode, and if we want to graph what 2 sine theta looks like, I'll just go to my y equals menu and just do 2 sine theta. Okay, and we'll see it just makes a little circle above the x-axis like that. So if we draw a picture, we have like, well, you don't necessarily know it's a circle, but it is. So when we're trying to find the angle from 0 to pi over 4, so it's saying like, okay, we start here at 0, and then we go out to pi over 4. I find it really useful to draw those. That shows me like, okay, that's the area I'm trying to find. That's the part of the circle I want to find. Okay, so, this is like my theta 1 and my theta 2, or my a and my b. So I'm just going to do, my area is 1/2 integral 0 to pi over 4 of 2 sine of theta squared. Okay, and again, when you see like a polar problem and you see an area, you should immediately think, okay, polar area, I'm integrating 1/2 r squared d theta. Like you're going to use that every single time you're finding a polar area. Okay, so how do we do this integral? Well, I'm sure some of you remember the formula, of course, that sine squared theta is equal to 1 minus cosine of 2 theta all over 2. Most of you probably don't, so you should just do this on your calculator. So let's go ahead and use our calculator to go ahead and find this area here. And when you do an integral, I can point out that you can be in polar mode or function mode. I mean, if you're feeling spicy, I guess you can be in parametric mode. But the mode that you choose for an integral is irrelevant, right? It doesn't matter. So when I go ahead and do this integral, I'll put the 1/2 here, but I could have just put it in front too. I just forgot, honestly. So 1/2 times, and then we have 2 sine theta. And again, you could just put an x there too, it doesn't matter. And that 2 sine thing is squared. And then my x is going from 0 to pi over 4. And because these things are squared, almost always, they're going to be something you need your calculator for. So anyway, we got 0.285. Writing 3 decimal points as always, of course. Okay. So let's go ahead and look at some other ones. So for example now, let's do, I think I have 2 more here. So let's say we have this following picture. And a lot of times you'll be given a picture. And the picture kind of makes a slug that looks like this. And this is the graph of r equals theta plus sine theta. And we're going to shade in this area above the axis and ask you to find the pink area. So one of the challenging things in these problems is figuring out the bounds. But hopefully you can see we're starting at 0, we're working our way around until we get to pi, right? So in this case, I'm just going to do 1/2 integral 0 to pi of r squared, right? So in this case, this is my r formula. So I'm just going 1/2 0 to pi of theta plus sine theta squared d theta. And again, we'll just plug that in our calculator. Okay. So that's how you set up a problem like that if you're given a picture and you could just see the bounds. One other example, if I give you a problem that looks like this, and I ask you to find now the pink area, and again, let's say this is some r, we don't know what the formula for, and I ask you to find the pink area. Think about what the bounds might be for that. Okay, now I think it's tempting to say, here's 0, here's pi over 2. here's 3 pi over 2. You might want to think that, oh, I could just go pi over 2 to 3 pi over 2, but that would be the left side. That's not what I want. So if you're looking at a problem like this and you want to find the bounds, remember that you need to go counterclockwise. Okay. So if you're going counterclockwise, it doesn't make sense to go 3 pi over 2 to pi over 2 because that would go in the wrong direction. We don't want that. So how else could I write 3 pi over 2? Well, remember, this is just the same as negative pi over 2. So always remember that. The 3 pi over 2 is the same as pi over 2. Pi over 2 is the same as 5 pi over 2. You can always like add and subtract 2 pi. So I could go like negative pi over 2 to 0, and then 0 to pi over 2. So if I wanted to find this pink area in this case, and obviously I didn't give you a curve, I'm just talking about the bounds here, that would just be the integral from negative pi over 2 to pi over 2 of 1/2 times whatever that r squared is. So that would be the setup that you would use in a problem like that. Okay, the last problem I want to talk about was flowers. Okay, so let's say in this case I give you, for example, find the area of the flower r equals the sine of 3 theta. Okay, and I'm going to talk about the approach to how you would actually go ahead and do this. Okay, so you graph it on your calculator, you look by hand, and one of the things that you might not be able to see is it actually traces the function out twice. So it draws it out, and it looks like this. It goes up and down and around, and then it actually goes around again. So it repeats. So this is a great real life problem because if someone gives you a flower for like a date or prom or whatever, you might just be thinking, well, this is a great flower, but I wonder where the area is. And now with polar, you can find, I'm also going to redraw because this is just god-awful. It goes through the origin a bunch of times. And it's symmetric. That's what it looks like. Okay. So the way you want to approach these flowers, the flowers cross over each other. It's like a parametric graph that does that. The way you want to find this is the whole area is equal to 3 times the area of the petal. So our strategy is we're going to find the area of one petal and then multiply that by 3. Obviously my picture is crappy, but it is a truly symmetric one. Okay, so how do we find the area of a petal? Well, obviously that's going to be 3 times the area of a petal is 1/2 integral of r squared. Remember, always integral 1/2 r squared d theta. So we're still integrating sine of 3 theta squared d theta. Okay, now the question you need to consider is what are the bounds? And that's what makes these kind of problems challenging. Now, the way we're going to find this is we find one petal. So say this pink petal. Now, I hope you guys can see, looking at the picture, the petal begins and ends at the origin. The petal starts at the origin, and then it like loops out, and then it comes back to the origin. Okay, so the petal starts and ends at the origin. And remember, if we're at the origin, that means that r, the distance from the origin, equals 0. So what we're going to do is we're going to set r equal to 0, and then we're going to solve to find the bounds. Okay. So in this case, my function is sine of 3 theta equals 0. Okay. Now, you probably haven't solved something like this since Algebra 2, but let's talk about how do we solve this. Well, how do we solve this formula? Well, we remember that if you just have the formula, where does sine theta equal 0? Well, theta happens to be 0, so that sine is 0 at the starting point and on the left side. So that happens at 0 and pi and 2 pi and 3 pi and so forth. So every pi, it starts at 0. So when we say, where does sine of 3 theta equal 0? Well, what that means is we're going to set the inside to equal 0 or pi or so forth. So we're going to say, okay, sine of 0 is 0. Sine of pi is 0. Sine of 2 pi is 0. So I'm going to set that 3 pi to equal 0, and 3 pi to equal pi, and 3 pi to equal 2 pi, and so forth. And then if I want to solve for theta, what I'm going to do is I'm going to divide by 3. And that's going to give me the bound. So that's going to give me all the points in this case where the r is equal to 0. So it's going to say that happens at theta is 0, and then pi over 3, and then 2 pi over 3, and so forth. So you're just getting more points where that happens here. Okay, So in this case, we're just trying to find the first bound. We see this is 0, this is pi over 3. So if I just want to find one petal, I'm just going to go, okay, from 0 to pi over 3. Now I'm not going to solve this, right? This is just 3/2 integral 0 to pi over 3 of sine of 3 theta squared. But the key on a problem like this with the petals is just to find one petal like I've done, and then multiply it by 3. And the way you find one petal is you say, okay, the petal starts and ends in the middle when the r equals 0. And then we just had to solve this equation, right? Where does sine equal 0? Sine equals 0 when this inside, the part that you're taking the sine of, is 0. Or you take the sine of pi, or you take the sine of 2 pi, and then it was just solving for that. Okay, so that's polar area. Thanks for watching. I'll see you guys soon.